Okay, Assalamualaikum and good afternoon. So today we start to discuss about boundary layer. So the whole chapter 4, 5, and 6 we will discuss about the boundary layer and its extension about boundary layer. So why we continue our study about boundary layer? It is because so in previous chapter, in chapter 1, 2, and 3, so we are discussing about, we have a plate here, and then we have a fluid flow, for example, from the left to the right, and we imagine that fluid has a lot of molecule here, and one of the big, assumption is that the real phenomenon is there is a no slip condition here. So the no slip condition here, so will make the velocity of this molecule become zero. So mean this molecule will stick to the surface, on the surface very well, and the velocity here is now equal to zero. And then what happened? So I think you already know about this one. That's why we could draw a velocity distribution like this. So we have a velocity distribution like this, and this velocity distribution is actually become bigger and bigger when the distance of the uh, surface here increase. Okay, so another thing that you should know that this no slip condition here is actually showing that this molecule has a shear, and this shear is actually could create force. So because we know that a force is equal to tau and A, so means that if we have a surface, so the total shear stress that acts on the surface will create force. So in the Navier-Stokes equation, we also discussed about the existence of shear stress, the existence of shear force. So and this shear force is actually also can be feel if you the simple one that we learn in chapter 1 to 3 is, for example, if we have a fixed plate and the moving plate like this, so and then if we have an liquid between these two plates, so and then if you want to pull this plate, you need to pull with certain force because the shear from this liquid give a resistance. Okay, so that's the idea. And then so this is the situation about fluid moving between two plates or fluid moving inside the pipe. So another thing, so fluid, if you see the fluid move, okay, the fluid flow, we are actually can be divided into two category, two types. One is fluid flow inside or between two plates. So we have two plates or we have pipes, flow in pipe. So flow in pipe means that the fluid is inside the pipe here, and then it surrounded with a solid, with a metal, with a plate. Okay. And another situation is an object. So for example, we have a submarine here. So and then this submarine is actually surrounded by a fluid. So this situation also is the situation where the fluid flow over an object. So these two, okay, in chapter 1 to 3, so we are focusing in this situation. So we have a fluid and it's covered or it's flow between two plates, between two solid object. But in chapter 4, 5, and 6, so we are discussing about when a fluid flow over a body like this. So because at this one, we cannot use the idea of co-wave flow or Poisson flow because there are no limits for the liquid. So for chapter 1 to 3, so we have a co-wave flow, we have a Poisson flow. So we could easily take a boundary limit here. So because we have these two solid. So For this one, okay. So for this one, I think you already know about this one. So normally when we have a velocity distribution like this one, we could say that if we connect all the, it will become like this. If we connect the maximum point of the velocity distribution here, so we could create that a layer like this. So this layer is actually called a boundary layer. So I think you already know about boundary layer in your undergraduate study. Did you learn about boundary layer before?
Yes, sir.
Okay, so Mane, it's quite easy for you to understand this topic, because for the first one we will use the basic idea of boundary layer, and then we will go for the extension for these topics. Okay. So we could shortcut the introduction. Okay, we could go faster. So means, so the boundary layer. So you know how the definition of the boundary layer. So the boundary layer will give us drag. Means drag here is the resistance of flow. So means that you need to overcome that resistance first, then you could flow. So but this drag, this friction, this resistance. Okay, this resistance is actually, some of them is good for us because it will it will lead to the existence of drag force and also the lift force. So the lift force here will help us to fly. Okay, and the drag force here is actually the resistance that we need to overcome when we move forward. Okay. So then I shortcut the explanation here. So if you still remember, to solve boundary layer, we need to know the velocity distribution inside the boundary layer here. So that's why in chapter 1, 2, and 3, we are explaining how to get the velocity distribution. If you go through, if you do revision for chapter 1, 2, and 3, so the whole story is about, we use the Navier-Stokes equation, we get the velocity distribution. Whether the velocity distribution, it is u equal to blah, 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 or we write as u over capital U. So in boundary layer, we will use the U over capital U here, but in chapter 1 to 3 in Navier-Stokes equation, so we just use the small u. So I will explain it later for this topic. Okay, so what is the u that we calculate in previous topic? So it shows the velocity distribution inside the boundary layer. Why? Because we need to know the velocity distribution, then we could estimate the shear stress here, and finally we could get the drag force and also the lift force. Okay, that's uh, the continuation from the chapter 1 to 3 with the chapter 4, 5, and 6. Okay, so this situation, it's only can be achieved if we assume the resistance is exists. The resistance means the viscous effect is exists, because in some calculation of ideal flow, okay, because previously I introduced you the ideal flow, we have linear, source, sink, and vortex. In some ideal flow, you need to determine whether it is rotational flow or irrotational flow. So if it irrotational flow, so mean that the zeta is not it's equal to 0, you could continue your calculation with ideal flow theory. But if you determine that the zeta is equal with certain numbers, so means it is a rotational flow. So mean the rotational flow means your flow now will have boundary layer. So you may refer to the previous notes that when I explained you about the rotational and irrotational. So now we assume that we want to see what happened is actually in the boundary layer. Okay. Okay, let's say if we have situation like this. Okay. For example, the basic idea is we have aerofoil like this. So and then we have the flow from left to right like this, and for sure we could determine, we could have the component force of drag force parallel with the x-axis here, and also the lift force on the y-axis here. So and then I think you already know this relation. So the drag force is actually the total of force that works on x-axis, while the lift force is the total force that acts on y-axis. Okay. So again, the idea is, okay, for example, we have a small area like this one. So we have a dA here, and then we have a free stream velocity. So we call this a free stream velocity. Okay, we have a free stream velocity. So it is shown in textbook in common symbol. It is a capital U. Okay, a big U, a capital U. But to differentiate my handwriting, so I will use a U with a bar on it. So we have a U and bar here. So when I write U, so it is a small U. Okay, and if I write U with a bar like this, so it is actually the capital U. Okay, so please differentiate the meaning of this one. So this it doesn't mean the average velocity. So it is actually the free stream velocity. So what is the difference between small u and capital U here is, so the small u is actually the velocity inside the velocity distribution. So we have distribution velocity distribution here. So U is actually the velocity for each molecule inside the velocity distribution. However, the capital U here is referred to the free stream velocity, mean the velocity that comes to the plate before it change into the velocity distribution. So for example, if we have a plate here, so the velocity before it's connect or it's make contact with the plate is capital U. And when it's touch, it start to contact with the plate, so it will create a boundary layer like this because the velocity distribution is start to occur. Okay, and then the velocity inside the velocity distribution here is a small u. So and then this velocity distribution is actually will become again as will become the free stream velocity after at a certain height. So this value, this velocity also is written as capital U. Okay. Okay, that's the symbol. So and then if you know that if we have velocity, so according to the Bernoulli equation, so when the velocity increase, the pressure is decreased, and vice versa. So when the velocity is decreased, the velocity will increase. So means that the existence of U here will lead to the pressure. So and then pressure will act on the area here, so it will give force. So means that according to the Bernoulli equation, so we could have force according to the pressure. So in this situation, we will have force due to the pressure, which is F is equal to P times A. So and then the fluid here, whether it is liquid or gas, so it carries viscosity. So the properties, the fluid properties has viscosity, and the viscosity will create shear. And then from that shear, the no slip condition, so mean the shear stress there, from the shear, so it will lead to the shear force, and then we could write, due to the fluid viscosity here, we could write another force, which is F is equal to tau times A. So mean in this situation, we have two forces. So let's say So the force from the pressure acts like this. So you know that pressure will push on surface, and the shear stress here will act like this because it's depend on the movement, moving direction. So and then as you know previously, as I said, that in we need to sum all the forces for x axis to create to calculate the drag force, and to sum all the forces on y axis to calculate the lift force. So we force is the vector, so we need to solve it according to its axis. So here we could split the force from the pressure here with to PA cos theta and PA sin theta, and at the same time the shear stress here can be split into tau A and sin theta, and also tau A and cos theta according to its own axis. So and then uh, to calculate the lift force and drag force, we could use this equation. So we have the drag force. So it is the summation, mean the integral process, the lump sum, uh, the summation of force that come from the pressure, and also force that come from the shear stress. And for the lift force, is the summation of force on y-axis. And again, so this is the force from the pressure, and this is the force from the shear stress. So and then from this equation, we could easily say that the value of P pressure here is can be measured. So I think in your previous study, in your undergraduate study, you know how to build your own manometer tube. You know you already practice how to measure pressure on a flat surface, and so on and so forth. So mean pressure on that surface can be measured experimentally. Okay. So and then the cos theta is also can be calculated, because you could measure the inclined degree angle, the inclined angle of that plate, and the dA here means the area of that plate. It also can be measured. You can use your tape to measure what is the width, what is the length of that aerofoil, and so on and so forth. So that means that you could calculate the dA here, the area. So for the shear stress, the sine theta and the dA here, it's settled. We could measure it, but we have problem to calculate what is the value of shear stress. Okay, because the shear stress here is actually the in simple words, we need to know what is the strength. Okay, what is the force that stick this molecule on the flat surface. So we need to measure this shear stress, the shear, the strength of this stick. Okay, so this is a big problem is actually. So to solve this equation means to get the drag force and also the lift force, we need to do something with the shear stress here, because the shear stress here is not easily measured. So we need to estimate with our calculation. So and the shear stress here is actually, it reflect the velocity distribution. So means that we have a velocity distribution. This velocity distribution is actually occur because the existence of shear stress. Okay, so means that from here, our aim, our basic target, our objective is actually to calculate the drag force and also the lift force, because this is the element that we need to know when we design something. If you want to design an aerofoil, so you need to have a large lift force, or if you want to design a car and so on and so forth, so might be you need to something that reduce your drag force. Okay, however, you need to know the shear stress, the tau first, before you could solve this equation. So now we go to the next step. We need to calculate, we need to find a way, a method to calculate the shear stress. Okay, so and then this is the basic formula. So I think everybody knows this one. So you will have a drag force. So it is equal CD times 1 over 2 rho AU square. So we have for lift force, we have CL here. And the A here, the area here is actually depends on the situation. So as I said, for example, if you have an aerofoil like this, okay, I'm sorry. So this, for example, we have an aerofoil like this, might be the area is actually, it is okay for us to calculate the length here time with the width here. So the area is actually the 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 area of a square of a rectangular shape like this. Okay, so it's depend on the definition. So it's changed. If you do research, it can be anything. So some people they will get this is the length of span, for example. So they just take this one and time with the width here to get the area. Okay, so but please remember this equation because this is a very equation, the basic equation to calculate the drag force and the lift force. So this is what I said. So please be careful about the area there because, for example, for the falling sphere, so we take this is the area, and the falling cylinder we will take this is the area, and if we have a falling cylinder like this one, we will take the area of this one as the area to be calculated in the equation that we mentioned in this slide. Okay, and now you need to understand that yes, we are going to calculate the drag force and the lift force. So we focus on the drag force first. But okay, in a specific way, in specific calculation, we actually could divide that drag force into two types. One we call it as a drag force, drag form, or another one is we call it as a skin friction. So actually the skin friction is something that caused by the shear. Okay, but the form drag here, the drag force is actually is caused by the surface area. Okay, so for example, if you see this situation, you have a very thin plates like this. So we assume that the thickness here is not so thick. It is very thin, might be 0.5 mm. So the area that resists the flow here is very small. But the resistance will come because the molecule will stick on the surface here, and then it will create a boundary layer. So, and then this resistance is actually, we call it as a drag force because the overall calculation can be calculated by using FD CD times 1 over 2 rho A N U square. Okay, so but to be specific, it actually the skin friction because this friction is actually comes from the shear stress. So, and then if you see the uh, image picture here, so if we have an aerofoil like this, so we could say that might be the drag according to the surface to the thickness of the aerofoil here is 10%, and the rest is the skin friction. So might be if you have this one, okay, might be you could say it is a 90% of the resistance come from of the surface, because you could imagine that all the fluid flow here will stop with the area of this sphere. So only 10% comes from the skin, from the surface. And then if the same plate like this, and then you change the orientation and become vertical like this one, so maybe so the total drag force is actually come from the surface, because the area here will give more resistance compared to the shear stress. Okay, that's why in this I think you still remember about the boundary layer that you learned previously. That's why we will discuss about the boundary layer here with the thin plate. So the condition that we always use is thin, flat plate. So because we want to neglect the effect of the formed form drag here. So mean we want to neglect, we just to make sure that all our calculation is based on the changes of shear stress, not the influence of the surface. Okay, so this is the very basic idea of a boundary layer. So okay. So what is boundary layer? So I think you already know about this one. So boundary layer in fluid mechanics is a thin layer of a flowing gas or liquid in contact with surface, such as that of an airplane wing or of the inside of a pipe. The fluid in the boundary layer is subjected to shearing force. Okay, as I said previously, so it's come from the shear force. A range of velocity exists across the boundary layer from maximum to zero, provided the fluid is in contact with the surface. Boundary layers are thinner at the leading edge of an aircraft wing and thicker towards the trailing edge. So this is the idea of boundary layer. It's become thicker and thicker, and the boundary and the velocity distribution is actually growing along the plate. The flow in such boundary layers is generally laminar at the leading or upstream portion and turbulent in the trailing or downstream portion. So this is because boundary layer is quite difficult to the experimental work of boundary layer is quite difficult to conduct in normal lab because the thickness of boundary layer is very small. So if you have, for example, 3 meters flat plate, you may have boundary layer at the trailing edge at the end of the plate of 3 meters. It's around 1 or 1 point something millimeters. So if you want to measure, uh, might be around 1 to 3 millimeters. I'm sorry. So and then if you want to put your pressure measurement to measure the pressure inside the boundary layer, it might be could ruin the boundary layer. Okay, so that's why if you search about how to measure or how to visualize the boundary layer, so people will do a lot of things. So some is they try to reflect the boundary layer with a mirror or the hot image. So I think if you search in YouTube, you could see that we use reflection of uh, we use a light to reflect the boundary layer. So please search boundary layer experiment from YouTube videos, and you will get a lot of not so high technology, but the tricks to do boundary layer experiments. Okay, so and then as we mentioned just now, we have a lamina and boundary, lamina and turbulent. So first, the flow is lamina here. So and then it will change into a turbulent. So in our first chapter, might be in chapter 4, I think. So we will focus on the lamina boundary layer because in certain application, only lamina boundary layer will occur. And then we will go about the turbulent boundary layer, and then we will try to we try to estimate the separation point. So the separation point here. So because the separation point here will create a wake. Okay. So wake is not a bad thing. In certain application, the separation need to be we need to prolong the separation, or we need to make it faster. We push to have we manipulate the surface area, the surface roughness, and so on and so forth, so to make sure that the separation can be occur earlier than its normal location. In certain application, we will push it. We don't want any separation because separation is actually can reduce the lift force. Okay, so that's why we have a stalled flow here. So means if you have if you are a pilot, So if you are pilot, so it's very dangerous if your airplane is in stall condition, because in stall conditions there are no lift force. So means your flight is actually not flying; they are falling down actually. Okay, so that's another story about the separation. But please try to gather information about the boundary layer experimental works and the separation point and so on and so forth. Okay, so uh, okay, so we stop at the boundary layer thickness. For this is the last slide for this one. So and then so first, there are three terms that you need to understand. So first is the boundary layer thickness, and then we have the okay, we have first boundary layer thickness. The second one is displacement thickness, and the third one is actually the momentum thickness. So we go for the first term first. So the boundary layer thickness. So the boundary layer thickness, okay. So it's show as delta. So you may write like this. So this is the delta. Delta means the thickness of the boundary layer thickness. So what is the definition of boundary layer thickness? It is a distance from the surface where the local velocity equal 99% of the free stream velocity, capital U. So means that, so the idea is if you have a flat plate like this, so we have the no slip condition. So mean the molecule will stick very hard here and not moving. So and then it will create a velocity distribution. And again, as the description, so the velocity distribution, it will become larger and larger, larger and larger, and finally it will have something like this. And then if we create a locus, so we plot a distance of the molecule here. Okay, first you know that the free stream velocity is actually the velocity that not make any contact with the plate. So we call this free stream velocity as capital U. And again, my handwriting will write as like this, U with a bar on it to differentiate the small u and the capital U. So, and then we in this velocity distribution, so we choose the location of small u, which is 99% of the free stream velocity. So you could imagine that in this velocity distribution, so this is 0. So and then so this is might be 10% of the free stream velocity, 20%, and so on and so forth. So finally we have a 90% here, and then we pick the location of 99% of u from compared to the free stream velocity. So we pick all that location, and then we connect all this one, and then this is the boundary layer. So this is the boundary layer region. Okay, so this is the formation. I think you already know the formation of boundary layer, and this is just a revision might be. So the first, we need to know the idea of boundary layer thickness, and the boundary layer thickness is actually in real life is actually the thickness from here to here, means from the surface to the location where the local velocity means the u here, okay, the molecule of u here, and the location of u that have 99% of the free stream velocity. So it is 99% from the capital U. So that is the definition of boundary layer thickness. Then another thing that you should know is, because it is a thickness, it can be measured manually. In experimentally, we could prove the boundary layer thickness. Okay, so means that the unit of this one is actually in meter. Okay, so boundary layer thickness is a real parameter. It can be measured in real live. It can be we could conduct an experimental to measure the boundary layer thickness. So means the unit is in meter, but the thickness is very small. So sometimes we use millimeter. So this okay. So but the unit the SI unit for this one is actually the length. So it is in meter or in millimeter. Okay. So and then this is the definition. So we need to transfer, we need to show this definition with the mathematical expression. So the mathematical expression for the boundary layer thickness is like this one. So we write delta is the boundary layer thickness. It is equal y. So why it is equal y? Because it is the distance. It is just a distance in meter, in millimeter, from the surface to the local velocity. So mean it is the distance of y axis. So means that we write delta is equal to y, but we put a condition. So y from 0 to u, which is 99%. Okay, some people say 99% of capital U, but some people will write delta is equal to y, which is u is equal 0.99 of capital U. Okay, please make sure that you write the capital U clearly. Okay, I suggest you to write as U and a bar like this. Please do not U like that. Okay, so because it is not easy for me to differentiate your handwriting. So I usually propose to my student U with the capital line like that, with the straight line like that, so it will reflect the capital U here, which is the free stream velocity. So the meaning of that mathematical expression is showing here. So then, okay. So and again, so the boundary layer here can be divided, as I said previously. So it can be divided into laminar and also turbulent. So then the boundary layer thickness is actually can be measured at any location. At any location means that, for example, you have a situation like this one. So you could say that, the thickness of boundary layer thickness at x equal here is 1 centimeter, and the thickness of boundary layer at the trailing edge here, it might be 8 millimeters. Okay. Okay, so I think we will stop here, and tomorrow we will continue about the boundary layer, the momentum thickness, the displacement thickness, and momentum thickness, and later on we will start the calculation to find about the boundary layer.